right. Okay, then next, we conclude that F has a min local min, okay, and at the same time it's global at 1,0. Okay, uh, no minimum in this case. Sorry, no local max, nor global in this case. Why? Because, well, you see that if you look at this problem here, sorry, if you see this one, uh, this is a parabola, but paraboloid. Okay, so its value is going up here, going up there. Okay, so there is no global min nor max. Okay. Okay. So this computation tells you that the vertex of the paraboloid is 1,0, obtained at 1,0. Well, the thing is, the extreme point is not necessarily extreme. Sorry, critical point is not necessarily extreme. So in this case, this is the example. Okay. But if you recall, this is a hyperboloid. Hyperboloids. This is also polynomial, and it's differentiable, therefore differentiable. And the critical points only stationary. Okay. So if you set the partial derivatives and set equals 0, you get x equals 0 and y equals 0. Okay, so this is the only stationary. Then we check uh, whether this is min or max. Let's see. If you compute this one, f of 1, 0, okay, so this is negative 1 over a square, which is negative, right? And if you plug in 0, 1, okay, if you set x 0 and y equals 1, then you get 1 over b squared, which is positive. So this value here, 0, is neither min nor max. Okay. Because there's negative values here, there's positive values. So 0 is not min nor max. Okay. If you try to plot this one, see, this is from the video supplement that I not showed you. I given you the link a while ago, a few weeks ago. This is hyperboloid, okay? And at this point, 0, 0 at the origin, you see a saddle point, right? So this is neither min, because this is looks like maximum if you follow this uh, this path here. But if you follow this path, it looks like min. Looks like, not really min. So it is neither min or max. All right, so the thing is, How do we know whether it is max, min, or leader? So we have this what we call a second partial test, say partial derivative test. All right. So we assume that f has a uh, second partial, continuous second partial derivatives at p naught. So meanwhile, the p naught is the a stationary point, meaning that the gradient is zero. So you compute d. P is what we call the discriminant. See, what is discriminant here? This kind of magical formula here. You see, this is second derivative x times second derivative y minus square of this mixed derivative. So these are the conclusions. If the discriminant b is positive and there's a second derivative with respect to x and x is positive, then this you get a local min. If you have a same but the fx is negative, then you have local max. All right. So what does this tells you about? Uh, have you find anything similar to this one on one variable? Okay. We call this second derivative positive, and the value of the coefficient here is fx is positive. Okay. So this looks like the second derivative test for one variable. All right. So find the d. Okay. When d is negative, then this is neither min nor max. Okay. And what this tell you further is that that's in P naught, you have uh, a saddle point. Okay. All right. Well, it's stuck. Okay. When this is zero, then no conclusions. All right. So why is no conclusions? Okay. Okay. We see that. Well, we skipped this a little bit, going back to our note yesterday. Okay. I also refer to the supplement. This is the shape of a quadratic polynomial. So if you have this quadratic polynomial of the form of this form, ax squared plus 2bxy plus cy squared, like this. Okay. And the thing is, if a and b are positive, okay, this is incorrect. This is C. Should be C. C. All right, here. So when you have this kind of equations, so no B here. Okay, so no xy term, only x squared and y squared. Okay, you have a paraboloid open up, and when a is negative, and this opens down. The key is that you try to identify the coefficients and see the sign. If both positive or both negative, okay. If uh, both positive, then you have paraboloid, or at least one of the coefficients positive, because this must be the same sign. Or you have this. In this case, you have min. This case, you have max. Okay. If you have a this form, so you see this is only ax squared, so no b, no c either. Uh, Here's the form. So it should be max in this case, but it's not the only max. Okay. So max, all the maxes along this boundaries here, along this line. This is along this line here, this min. Okay. Sorry, it should be C. Let's take it here. This is C. So when you have A and C of different sign, then you have a saddle point. Okay. And how to distinguish them? Okay, use this formula here, D, same D. So this AC minus B squared. Okay. If you have a D positive, then you have this or this one, paraboloids, opens up or opens down, depending on the design for A. A positive mean it has opens up, mean it has min. A negative, it has paraboloids opens down, so means the vertex is the maximum. If D is negative, then the point here is neither min nor max. But if D is 0, then you have this one. So the origin is one of this, one of the max is one of the min. Okay, so let's get back to slides. We have the same D here, but we have this formula. Uh, Quite similar, but also different with the D in the shape of parabola. So what does it has to do with the shape? Okay. And the conclusion seems quite different also. 1 and 2 and 3 is quite the same, because when D positive, you have min. When D negative positive, one of the coefficients here, like second derivative test. D is negative, then this you have a saddle point. But conclusion 4 is quite different. All right. So before explaining why you have this formula, so let's do some example. All right, so we need to find the extreme for this function. This is polynomial cube, polynomial cubic. So this is polynomial. So it satisfies the second derivative test. Second derivative. This is the assumption for second derivative test. Okay. First, we need to find the critical point. The critical point is the stationary in this case. So derivative respect to x, derivative respect to y, set them equal 0. Okay. So if you compute this one, this 9, you factor the 9 out, you get x squared minus 1. You factor them out, you get x equals plus minus 1, right? But then at the same time, partial derivative with respect to y, 2y minus 4 must be 0. Okay, so you get x is 1, negative 1, and y is only, the choice is only 1. Ay equals 2. So this is it. All right, so we got two critical points. Okay, so we check the second derivatives. This is compute the second derivatives. That's easy. 18x for second fx. Fyy is 2, it's 0. So then if you compute this discriminant at the point negative 1 and 2, you get negative. But if you plugged in plugged in 1, 2, the other point, you get positive. So what's the conclusions? So according to the theorem C, this is the theorem. F12 is because the discriminant negative is a saddle point. So it is neither max nor min. While the second one is it has a local min. Why? Because you have this. This coefficient is 3 positive. So the shape is closer to 1, 2. It looks like a paraboloid. Okay, opens up. So this point looks like the vertex of the paraboloids. Okay. All right, so now let me explain how you can justify this formula. Why this formula looks like uh, this formula here looks like this one for parabola for second sorry for quadratic polynomial of this one. All right. Okay. So this is sketch. So you assume that the this one origin, okay, and also assume that fp0 is 0, okay, and the gradient is 0. So this is critical stationary point. Okay. Stationary. So this is if this happens not to be 0. Okay. So we translate f. You subtract one at. So making the fp0 equals 0. Okay. So move up and down. Okay. So we look for the Taylor uh, second order Taylor for f around p0, p naught. Okay, so we call it the Taylor polynomial for this is of this form. Okay, so this one we had yesterday. Okay, so fxx x squared fx2 x the mixed derivative and fyy for the coefficient for y squared. Okay, there is no order one. Why? Because this is stationary, so we assume this is stationary, so the gradient is 0. And first order is, we call it first order is this. Okay, so this is the first order. But because this is 0, then the first order must be 0. So we only have, and we assume this is 0. Okay. So really the Taylor polynomial is this one, the second order one, right? So if you talk about the Taylor approximations, so this will be equal to this one plus some error. We consider this, the remainder is the error. Okay. All right. For p equals to near p0, then the value of f is approached by the Taylor polynomial. Okay. So this is the picture approximation. This is the f as z equals f, so the flatter one. And p0 is this one. And near around p0, it is approximated by the Taylor polynomial is this one. It's paraboloid. And this point is the vertex, the min of this paraboloid. And we would like to conclude that this is actually the local min also of the z of f. Here's the same f before. Right. Okay, so let's we call this form 1/2 ax squared plus 2 bx squared. So here, if you compare this form and this formula here, that's exactly the same, right? With a is fx, second derivative of x, b if fxy, mixed derivative, c is fxy. Okay, so from here, if you do completing the square, you you try to compute this a and first and second terms there. You get this one. You know, you can compute it. That's easy. All right. So you see, this is a square. This is a square. So depending on the side. Okay, so this is really dependent on uh, the value of a c minus b squared. So what is a ac minus b squared? A c b squared. Okay. So we get this formula. So for discriminant positive or discriminant negative. All right. However, when discriminant is 0, okay, the Taylor for this one, the Taylor polynomial looks like a parabolic cylinder. What is parabolic cylinder? Parabolic cylinder is the shape like this one, or this one. Okay, so this one, f at the 0, min or max or neither. Okay, so this tells you that, well, that depend on the this a remainder here. Okay, so we cannot tell whether it is max or min. Apply this the second order only. Okay, so this tells you that that's why the uh, second derivative test doesn't give you conclusions. Or as a fact that you need to know that when you compute Taylor polynomial for another polynomial of f, then the Taylor is the same as this one. Okay, it doesn't change. All right, so look at this function here. So this is power 4. Okay, uh, if it were the 2, then you have the x squared plus y squared. We know this paraboloid. Okay, so now you know the vertex is negative. Sorry, it's min. But in this case, this is power 4. So it should be min though. But if you compute the Taylor second order polynomial, the Taylor, because this is polynomial, the Taylor is also the same, power 4. And you see, it is power 4, order 4. No second order. No second order, meaning second order is completely 0. If the second order is 0, then the discriminant is also 0. Okay? Discriminant 0, then you have no conclusion for the second derivative test. Right? But you see, because this power 4, this has no negative values. It's always non-negative. So you see the vertex. This is the minimum local min. Okay. But in fact, this is power 2, which is 0 plus the remainder. If you plot the diagram, you get this picture. I call it super paraboloids because the paraboloids is power 2. So this is the negative, sorry, the min, local min. Or you have this function here. X squared minus y, sorry, x to the fourth minus y to the fourth. Okay, what do you expect? It looks like a hyperboloid, but how do you know? How we know this one? All right, so let's look at the Taylor polynomial around 0, around the origin, is the same. Right? So the second order, Taylor second order is 0 because there's only power 4, no power 2. So the power 2 is equals 0. Now, because it's 0, then the gradient, sorry, not the gradient, this is the discriminant is 0. Right? If you plug in 0, the value is 0. Plug in 1, 0, you get 1. But 0, 1, you get -1. So this protects is neither min nor max. Okay. In fact, this is the plus remainder. Okay. See this one here. The super hyperboloids. Okay. So you see for this case, discriminant 0, then the behavior, whether it's extreme or non-extreme, is dependent on the remainder. So you have to see the higher order Taylor polynomial. Okay, so second order is not sufficient, not enough. All right, we'll do some more example for this. Let's finish this one up. So you have max min. So find max min of this function on this one. Well, this is rather restricted to this area only. Okay. All right. So this one is called this an ellipse. Okay. This ellipse. So you see here would look like for a uh, maximum on this. This is the picture. So not the whole hyperboloids. Uh, F is polynomial, then the critical point is only stationary. Okay, and now because we have this area here, the region, so we have suddenly have a, a boundary, and the boundary is this ellipse here, but equals 1. So this boundary here. See? All right, so use the second derivative test. Find the gradient, set equals 0. So you get x equals 0, y equals 0. So you get this one. That's the only stationary. If you compute the discriminant at the origin, here you get positive. So you have a min, local min. So 2 is local min. Okay. Because you see this is a 2 plus x squared plus y squared. So 2 is really the min because x squared plus y squared is non-negative. Okay, so this is the global min. So the bottom here for x. Okay. So how to find the global max? Looks like the global max would be in here, located somewhere here. Right, so it's boundary. So we look over the boundary. All right, so this is the boundary. This is an ellipse. Okay. So we put a parameterization for the ellipse by, let's see, think this ellipse as a particle, a path of a particle. So this is well, you see this quite often earlier for the parameterized equations. Okay. So in this case, set x equal cosine, and sine is 2 sine t. So pi from 2 to from 0 to 2 pi. So this x is y. If you substitute this to the functions, okay, so we get uh, so x is cosine square, so 2 plus cosine squared t plus 4 sine squared t. Okay, so you get, well, 1 over cosine square and sine square becomes 1, so it make the constant 3. And so what's left is 3 sine square. So this is what we have. Okay. All right, so let's try to find the max here for t. Uh, we don't need calculus because sine square is all, the least is 0, maximum is 1. T is maximum as when sine equals plus minus 1. Yeah, like pi over 2 or 3 pi over 2. Maximum value is 6. Okay, so this is how you do max min with a when you have boundary. All right. Before going to the model, let's think. This is the last thing here. Okay. Any question first? All right. We have a cable, uh, power cable from a power line, say cable, power line from a generator to a factory. The factory is located across the river. So position is the factory is 100 feet from the banks of the river. Okay, so the generator is the yes the generator is 2 feet. Uh, well, this is uh, upflow. So on the bank also. The width of the river is 50 feet. You assume there is no no bend between on the river, so this is straight. It's a straight flow. Okay. And assume the river is shallow. Why we need it shallow? Let's see. All right, so this is how to it is about cost. Okay. So the cost of the uh, power line installations underwater is 600,000, 100,000 feet on the banks of river, and 200,000 on land. Okay, so how do you install the power line so the cost would be minimal? So first the thing is picture. So this picture, where so we have a river. This is the power generator. power plant. So the factory. All right, so somehow you have to go cross the river and river along the banks and start moving on land. Okay, so let's see. Let's compute this. Suppose uh, you cross the river at P. So from from P to Q, cross the river. Q is X feet north of the P. So moving up north along the bank and then moving on land to the factory. Okay, so using this model, you see that the length of the path on the bank is 200 minus x plus 1. Okay, so based on this, we can find a model. So uh, there are three modes here. Underwater here, when it crosses. When it crosses, the length is 50 square plus x squared. Okay, so Pythagorean. With the cost 600,000, so it's just 600. Okay, and on the banks, there is 200 minus x minus y, and on land, this part is, so again, this Pythagorean formula. That's the cost. So you have this model. All right. So how do we model this one here? So because x, y distance, this must be positive. Okay, so x plus y is less than 200. Why? Because so make QR is still having positive distance. Okay, so if you model this one, x to y less than uh, 200, so this is 200, 200 is fine. Okay, say C1 here, C2 and C3, CX in the middle. So in the interior, you see the stationary. This is this one. Okay, you can try to find this. We'll see some example. So use the second derivative test. You see this one. So you get this the local min. All right, so that's the minimum local min. Okay, so you get the parameterize this one. C1, C2, and C3. You do this separately. All right, we'll go back to the slide later when we need it. So next we should give you some example, more example. All right, questions. All right, we pause here for about 5 minutes. Okay. All right, and let's take a break.